Attenuation, last class I discussed about what is attenuation, what are the numericals are important related to attenuation. So here today's class I will discuss how many types of the various attenuation concepts and mechanisms are there. Due to that we cannot get the exact signal at the other end of the fiber, right? So attenuation that can be divided into three parts. There are the three different concepts due to that attenuation may happen inside the fiber. So what is the attenuation told yesterday last class? So suppose this is the signal. So after certain period of time, you can see the signal strength is decreased continuously, right? So this is the concept of the attenuation. So there are the three mechanisms. One is the absorption mechanism, and the scattering loss, and the radiative loss, and bending loss. These are the mechanisms due to that attenuation may happen inside the optical fiber. And optical fiber will not get the exact output, whatever output we are getting in the inside input. Okay, so what are the input output I am getting, I'm sending into the one end of the fiber. Okay, so that I am not getting the at the other end of the fiber, so there is a reduction of the output. Okay, so what is the absorption? Absorption means that is related to if the light is propagated through the fiber, if the fiber has some materials and some other things, some imperfections are there. So this the exact amount of the light is not propagating through the fiber. Some amount of the light is absorbed by the material. Okay, some amount of the light is absorbed by the material. Suppose 5 milliwatt signal is propagating through the optical fiber. So from the side of one sinusoidal signal 5 milliwatt. So for 1 milliwatt signal is can be absorbed by the other material which is inside the optical fiber. So what are the reasons for absorptions? And the scattering loss. Scattering loss means the so once the light hits at the core cladding interface, light can hits the core cladding interface. Suppose light hits the core cladding interface. When it hits the interface, at that moment, some imperfection and some inhomogeneity is there. Due to that, rather getting light in the other direction. So this light should follow this path. Okay, but it is following the different path. Okay, so this is concept is called the scattering. This I will also discuss. Next, third one is the radiative or bending loss. So this is the fiber. If fiber may bend, okay, that time, so you can see at what point it is bent, so it is not following the proper total internal reflection, and bent point it is not follow the total internal reflection. Okay, so due to that also the signal may reduce, right? So the absorption, there are the intrinsic absorption, extrinsic absorption, atomic level. Intrinsic absorption means so the whatever material are used for the designing optical fiber, so this material can be the light can be absorbed by those material. Extrinsic means if some impurity is added during the fabrication, these are the extrinsic. And atomic level, so atomic defects means so when the some materials is designed for the is used for optical fiber, so in those materials some atomic defects are there. This is related to atomic defect. And intrinsic absorption again further divided into the infrared region and the so absorption may happen in two regions due to the some physics due to some physics. This I will discuss also. The scattering loss, this can be again I told that some fluctuations. So sometimes suppose gallium arsenide, right? So gallium x 1 minus x, right? This should be made, right? So imperfection means suppose instead of getting x we are getting the point 9x, here we are getting the suppose 0.9x. So in some point I am getting the gallium X arsenic 1 minus 6. In some point I used to get the gallium 0.9x like that. So this is the fluctuation. Okay. Next, homogeneity is this I will discuss also. The bending loss also can be divided into two parts. One is the micro bending, another is the macro bending. Micro bending and the macro bending. Now come to the absorption. This I told you the three concepts at the intrinsic absorption, atomic level, extrinsic absorption. At atomic level means there are some imperfection in the atomic structure of the fiber material. So whatever material is used for the fiber, that I told, whatever material is used for the fiber, in that material if some defect in there in atomic structure, so due to that some light can be absorbed by those atomic defects, those level, atomic level. So what are these defects of a missile molecule? So one fiber is designed for based on some molecule. So some molecules are absent. Here also some high density cluster and oxygen defects. If in a glass structure some oxygen defects are there. So this is the natural. You cannot do anything. You can modify something by processing the fiber. Right. These are the atomic level atomic defects. So due to that, the absorption can happen inside the fiber, but it is negligible as compared to the other absorption. So it is significant when the fiber you expose for some process. So for some process, if you expose the fiber ionization radiation, that this concept is the significant, this absorption. The next is the extrinsic absorption. This the extrinsic impurity. Extrinsic means normally it's not related to fiber, right? So impurity atom. So normally in some time it may happen that when you design the any fiber, so during the fabrication only some extra impurities and extra material can atom or, can doped inside the fiber. So these are the called as impurity. So the minor impurity, how this impurity can include inside the fiber, suppose some oxygen, OH ion. So when water is the glass is dissolved with the water, then some oxygen ion that can create the bond with the glass. The glass made up of the silicon oxide, right? So this can create a bond. The silicon oxide bond can create. So when, and again some transition materials, some iron, nickel, copper, chromium, vanadium, these are used for some other purpose, but somewhere this can dissolve with the this can create the bond with the glass, right? So these are the impurity may create a bond with the glass. So when the oxygen ion, this can create a silicon bond with the silicon. Suppose some oxyhydrogenation, some hydrolysis reactions are there during the fabrication process. That time the oxygen ion, OH ion can create, and this OH ion will be acted as the impurity which can create with the create a bond with the silicon. Right, so these are the some reaction. The silicon, say silicon chloride, for tetrachloride, say the germanium tetrachloride, like that. So if we see the attenuation profile with respect to the wavelength, here we can define as a three window: the first window, second window, third window. And normally this window is designed based on the low attenuation. When we call, if you think about the first window, here also you can see the attenuation is higher as compared to the this window as compared to this window. But this window is used for the when you want to design the plastic optical fiber. For this case, this window is used. So day by day, some research has had been done, and after that, these are the some wavelength range which can be considered as a second window and the third window. Here, some advantages are there, and then for third window, some advantages are there. So both cases you can the low attrition, but as compared to second window, you get the low attrition in the third window. So normally, this third window is used for the long distance optical communication due to the low attenuation. Intrinsic absorption. Now come to the intrinsic absorption. So intrinsic absorption is the basic property of the material or atom which is used for the optical fiber. So normally the pure, if we consider the pure silicon dioxide, so during fabrication no other material is doped or impurity is added in pure in silicon dioxide, only the pure silicon dioxide. So if the other impurity or some atomic defects are also not there, but we get some absorptions. Okay, intrinsic absorption will get. So intrinsic absorption may happen due in the ultraviolet region and the near infrared region. So we know that E is equal to AC by lambda, lambda G. Okay, G is the band gap of the material. This is the conduction band and the valence band, CB and the valence band, and the lambda G is the wavelength of the light which is incident on the fiber. So ultraviolet, sometimes what happened, Suppose the silicon dioxide as a material is used for fabricating the optical fiber. So this material itself can absorb the light. When it can absorb, suppose it has a one band gap, that is band gap. Suppose it has one band gap which is suppose near. If we calculate, if the UV light wavelength is propagated through the fiber, so you can calculate the band gap from the UV light, right? And if this band gap is correspond to the material band gap, so then the absorption happen. When the UV light is propagating through the fiber, the absorption may happen. Okay. And there is other concept, that is the silicon oxide. Some lattice vibration is also there. Due to some lattice vibration, so the electron can get energy from the near environment, and it can excite it, and it can go to the conduction band. So for this reason also, you can see the near infrared ray also the absorption may happen. So the electronic absorption, that UV absorption. So here you can calculate the UV absorption H. The C is E alpha is equal to C e to the power E by E. So this alpha, that attenuation under the UV region, that you can calculate it to the molar function of the material which is used for the fiber. This material, the conduction band, valence band concept I told that for this material. Okay, so if the light is propagated through the fiber, if it absorbed by the band gap of the germanium oxide, so it may absorption may happen, then the attenuation can be produced. So this attenuation can be calculated using this formula 154.2 x 466 x plus 60. So this x is equal to molar fraction of the germanium oxide. The lambda is the wavelength of the light which the light is propagating through the fiber. So the concept, this loss is called as a UV loss. UV loss under the attenuation. The infrared absorption, they say told that vibrating bond. So you can see under the conduction band and the valence band. So no, it's not related to this thing. Actually, it happened that so in the conduction band, valence band, there are the multiple bands are there, right? So sometimes it can happen. So the vibrate the some bonds are inside the material, right? So this bond may vibrate, and it can release a energy, right? It can release the energy. So the electron gets energy from this thing, and it can accelerate into the upper band, right? So due to that thing also the absorption may happen. So this is called as a infrared absorption. So this loss due to the infrared absorption, that can be defined as this formula. The lambda is the wavelength of the light, right? So one is the normally directly the electron goes from the conduction valence band to conduction band, that due to that reason UV absorption may happen, and the infrared absorption happen due to the lattice vibration or vibrating inside the bond, which can create the energy. So from that energy the absorption may happen. So in this left diagram, you can see that with respect to the wavelength, if wavelength is increased in this side, you can see the loss, UV loss is decreased. UV loss is decreased, right? And if you see the infrared region, so if you decrease the wavelength, then infrared region absorption is decreased. Okay, so suppose this is the decreasing loss, this is the increasing loss. Okay, so this value is increasing. Here you can see the with increasing the wavelength, you can see the region loss is also decreasing, and again with increasing the wavelength, you can see the linear infrared region absorption is increasing. Lower wavelength, near infrared absorption is less, but UV absorption is high. A higher wavelength, near infrared absorption is high, but the UV absorption is less, like that. Now come with the scattering loss. Scattering loss is a computational due to the compositional fluctuation and e-emergence. Compositional fluctuation, I told that the gallium. arsenide, suppose it is x in 1 is to 1 minus x. In somewhere I can use this material is properly formed at some location of the fiber. In other location of the fiber, rather getting the gallium arsenide, we are getting gallium 0.9x and arsenic 1 minus 0.9x. Okay, so this is the fluctuation composition. This concept is called the composition fluctuation. Due to that, you can see the light is not hits at the proper location and it's not reflected back from the interface of the core cladding. It is propagating in a different directions due to this compositional fluctuation. Inhomogeneity or defects in the fiber. So defects in the fiber, that's related to almost atomic level defects. Or inhomogeneity means, so the material density is somewhere is high. So in the fiber you can see the material is coated. Suppose one material is coated inside the fiber, so in some point the material density is high, suppose in some point material density is low. So due to that reason also scattering loss may happen. This thing is explained. So relay scattering, this is called because the why this sometimes if there is a compositional fluctuation in homogeneity, so that would happen. The reflecting index may change due to this reason. Due to this reason, the reflecting index may change. If reflecting index change in some point there is one reflecting index, in other point there is a different reflecting index. So for what happened for that? The light is the direction of the light will continuously change. Okay, continuously change due to the change in the reflective index, right? So this concept is called the relay scattering, and this is inversely proportional to the wavelength. So that's why I told that if you increase the wavelength, each and every losses will be decreased. So 50 nanometer wavelength is the most important wavelength which can use for the long distance communication. So this is the scattering concept you can see. So at this moment, rather transferring light like this way, it can directing in a different directions, and again it is returning back. Okay, so this concept is the scattering concept. So next the bending loss, micro bend and the bending loss. So suppose if the fiber is bent like this way, the curvature of the radius of the curvature is more. Okay, the radius of curvature is larger than the radius of the core. That is called the macro bending. So when it happens, so while if there is a fiber pole, so if the each fiber need to place inside the fiber pole. Okay, so during that time, so some bending loss may happen. So this micro bending means, so this is a fiber, so suppose a small bend is there in a cladding layer. Okay, small bend is there in a cladding layer. At that time this is called the micro bending loss. So this is happen mainly due to the fabrication. During fabrication, this may happen during fabrication, and this is handling during handling. During handling, this may happen. So macro bending, this I told that macro bending is due to the macroscopic effect, suppose bend of the fiber during handling. Macro bending is related to optical core due to the macroscopic effect like deformation and damage in the core cladding intervals. Due to that, the macro bending may happen. This I have already discussed these two diagrams. You can see. So this while bending the fiber like a cylindrical way, and this is a small bending for case of the micro bending. So poor reeling and the mishandling of during installation, the macro bending. You can see in case of the macro bending, this the electrical distribution. If bend is there, that point is bent, so it is curved fiber. Okay, bending happen in that point. So what happened? The power is not confining into the core. The electric field is distributed inside the clad also. So there is the loss in the fiber. At this point, there is a loss in the fiber. So micro venting, this this suppose during fabrication, some low temperature fabrication is there. So fiber is placed fabricated at very much high temperature, right? And non-uniformity is there during the fabrication of the fiber. So due to this reason, the micro bending may happen. So if you consider the physics behind the micro bending, so the mode coupling concept is also there due to the micro bending. So you can see for case of the macro bending. So this is the direction of the propagating light. Instead of getting like this way, it is getting in the different direction. That's getting in the different direction. Here also you can see the rather getting the uh, uh, so here also you can see there is a change in the direction. It's not following the proper total internal reflection. So if you put the proper jacket layer, so it can reduce the micro bending. So due to some pressure and temperature, if some bending may happen, that can be reduced if you put the proper jacket outside of the fiber. Again, if you place the fiber in fiber pole, so it should be like this way. The curvature, the radius of the diameter of the fiber should be large when you it placed on the inside the pole. Okay, so that time the loss will be less. So if you bend like this way, you can see the fiber will be break, and if you bend like this way, the high loss during handling of the fiber. So the bending loss is also sometimes is used for used for generating the optical power, or used for some application like a pressure sensor application. It is used. So if suppose temperature sensor, pressure sensor, for those kind of the application, the fiber optic can be used. So if the pressure is not there, how much power is getting? If pressure is there, so how much power is getting? How much pressure is applied on the fiber? So this pressure for the pressure sensor, this bending loss can be used. These are the core cladding losses. So the core cladding losses is somehow related to the scattering loss, but why it happened? Sometimes here also the cloud, if there is a change in the reflective index in core cladding due to the some compositions. Okay, so that time whatever amount of power should be distributed inside the core, so will not get the exact amount of power that should be distributed inside the core. But some power will be distributed inside the core, and some power will be distributed inside the clay. So this happened due to the change in the reflecting index for structural imperfection on the inhomogeneous composition or fluctuation in the composition. Uh, this is the loss is determined for the core cladding loss. The alpha 1 and alpha 2 alpha t, these are the loss for the core and cladding. The p cladding is the power distribution inside the cladding, and p is the total power for step index. And for gradient index, that will be the different. So in for case of the gradient index, we know that the reflecting index is varying continuously. It's not constant. It is really decreasing if you come from the core to cladding. Okay, core is there is a one reflecting index in the cladding core and cladding interface. There will be the reflecting index, but radially the reflecting index is changed. So due to that, also you will get the different losses, one for alpha 1 and on to alpha 1 alpha 2, that I told that the losses due to the core and cladding, right? And this thing is related to the reflecting index, changing the reflecting index inside the core and the cladding. So this is the formula for calculating the loss, attenuation loss inside the gradient index fiber for core cladding.